Uh, okay, hi everyone. My name is Dr. Salah Al Zaidi. I'm assistant professor in University of Baghdad, College of Engineering, University of Baghdad. This video lesson is a part of my lecture notes on structural dynamics submitted to master studies in our department. Today we intend to use CSI SAP to simulate, to prepare a finite element model and determine the natural frequency, fundamental natural frequency, and the fundamental period for the roof slab of this residential, this building. Okay. Here we intend to determine natural frequency with neglecting at this stage, with neglecting the weight of the generator to be supported on the roof slab. Later we will show in other lessons, in other lectures, we will show how the weight of the machine change the natural frequency of the system. To compare our finite element model with the analytical solution, uh, this system, this roof slab, will be simulated as a simply supported one. That does mean we implicitly neglect the torsional stiffness of spandrel supporting beams and the interaction between the deflection of a slab and shortening of the supporting columns. Okay. These assumptions have been included in finite element model to be able to compare with the analytical solution. From the analytical solution, using generalized single degree of freedom uh, system and with assumption of sine relay shape, we have a natural frequency of 260 radian per second and a time period of 0.02417. Okay, start the SAP 14 actually. Change the unit to metric system. Uh, Start a new model from grid only. Uh, the the roof slab will be simulated as a single panel. Hence, we will have a 3 meter, two grid along X, two grid along Y, and one grid along Z, as I intend to simulate the roof slab only. Regarding the spacing between grids, I have 3 meter to simulate the width of the panel. By the way, the panel, roof panel, is assumed to have a width of 3 meter, a length of 6 meter, and a thickness of 200 millimeter, and a compressive strength F sub C prime of 28 megapascal. Okay. Okay. I have these grids. Okay. Let us save my model. Penthouse. Override. Okay. The second step to change the imperial units, to change the 400 psi to be more suitable with metric system that adopted in specification. Young modulus can be determined from ACI relationship. Okay, I have 24870. 24870. Poisson ratio is default value of cross Poisson ratio is accepted. Thermal coefficient is accepted, not related, actually not related to our problem, and shear modulus modified according to strength of material and theory of elasticity. Finally, compressive strength of concrete changed to 28 to make the model more complete. Okay. Okay, I return to name, to use more indicative name of material, 28 megapascal. Okay. Go to okay, go to define slab section, slab section. Okay, I think I still have some problem in material. Okay, I will change the material later. Type of different models have been discussed previously in another lecture. Today we say no more about of them. Slab thickness is 200 millimeter. 200 millimeter for membrane. Okay. Okay. Return to material. I may have some problem in material. Actually, the material property seems not change. I have 24870 megapascal and have 28 megapascal. Finally, I will change the name to F sub C prime of 28 megapascal. Okay. Okay. Return to section to check. Okay, modify. Okay, correct material is adopted. Now use draw equip to equip the slab panel. Save my model. Okay. Go to view to select full object. Go to select full object. Both cases. Okay. And now I will define load pattern. When we are in the previous lecture, we are discuss what we mean with load pattern and load case. Load pattern, I will change the date to self. Okay. Modify. And then go to load case, the static load case, to change it into self to be more compatible with the corresponding load pattern. Then I go to mass. Three different types of mass simulation in SAP model have been previously discussed. I will select the load to be transformed to mass. Add. Okay. Maybe the main drawback in SAP simulation is that we cannot assign the reaction to the edges of slab we only can assign support to node. Therefore, we divide the slab. We enforce to divide the slab panel into segments. Unfortunately, these segments are irreversible in nature. Point 0.5 meter by 0.5 meter will be adopted here. Okay, okay. I select the edges, four edges, to assign hinge support. Okay. Finally, I go to load case, to model load case. We previously give a general description of what we mean with number of modes and that infinite element model. We transform the continuous system into a multi-degree of freedom system. Hence, from theoretical point of view, we have mode shapes equal to the number of degrees of freedom included of the model, and that from engineering point of view, we in general we need and we interest with the fundamental modes, the lowest modes, and we also discussed that SAP software select the first 12 lowest mode by default, and also we discussed that here we have here I mean with multi degree of freedom system, uh, that resulted from finite element simulation. In multi-degree of freedom system, we have mass matrix and stiffness matrix, and to solve mass matrix and stiffness matrix and determine the eigenvalue of the equation, we should solve a polynomial characteristic equation. Different algorithms have been developed to solve this problem, these polynomial characteristic equations. Two of them included in SAP eigenvector technique and Ritz technique, and we said that these techniques will be discussed later when we talking about the multi-degree of freedom simulation. Okay, at this point I select, for example, first four frequencies to adopt it in my model. Okay, okay, save my model. Finally, to focus on vertical mode shapes, I go to set analysis option and select XY plane. XY plane. Therefore, I will with this option I will focus on vertical vibration of the roof slab. Okay. Now, now I'm ready to run my model. Run my model. Okay, go to mode shapes. Mode shapes. Okay, this is the first mode shape with a natural frequency of 0.0246. If compared with analytical solution, I see that the generalized single degree of freedom with sign relay sinusoidal relay model. The analytical model is so close and so accurate if compared with finite element model. Okay. Thank you for your listening and thank you for your time.